Hello everyone, my name is Lawrence van der Maaten, and Awni, Hannun and I are excited to present our work investigating the trade-offs of private prediction. In machine learning, you often train your machine learning models on training data that needs to remain private, even if the predictions that that model makes on test examples are going to be exposed to the world. And this is the goal of private prediction. The goal of private prediction is to make sure that the amount of information that is leaked about the training data of your model by the predictions on test examples is limited. Now, if you look at the literature on private prediction, you'll find that there are many methods that perform differentially private prediction. But all of these methods are only studied in theory, and very little is known about their empirical performance. Which raises the question, if I have a practical scenario in which I want to perform private prediction, which method should I use? The goal of our study is to try and answer this question, as well as to investigate the trade-offs that play a role in private prediction. So before I dive into the details of our study, let me first set up the privacy framework that we use, which is a standard differential privacy framework. So for those of you who are not familiar with differential privacy, here's a quick introduction. Suppose we run a randomized algorithm on data. And this could be either a randomized learning algorithm or a randomized prediction algorithm. Now what differential privacy says is that changing one data point should hardly change the output distribution of this randomized algorithm. And so this is formalized in the equation you see below, which says that for all datasets D and D prime, which are datasets that differ in only one example, and for all outputs, the output distributions should be very similar. So in this case, D is a dataset, D prime is a dataset that differs from D in only one example. A is a randomized algorithm, a learning or prediction algorithm, and S is a set of possible outputs, a set of possible models or possible predictions. And what differential privacy is bounding is the probability of a certain output that cannot differ too much between the two datasets D and D prime. And the difference is measured in terms of a privacy loss, e to the power epsilon, where epsilon is the privacy loss, and an additional fixed term delta, which is referred to as the privacy failure probability. And so this is the framework that we'll be looking at in our study. But in order to use it in private prediction, we do need to adapt it a little bit. In private prediction, the assumption we make is that we train our model on private training data. So we want to get differential privacy with respect to that training data. And we're going to release predictions for B test examples. So B is our budget, our inference budget of test examples. And we want to limit the information leakage on the training data. And so this is formalized in the expression you see below, where theta of D is a model that is trained on the private data. And theta D prime on the right-hand side is a model trained on that same data, but only one different example. And the set of outputs here is referred to as Y, so these are the classes that can be predicted. Now X here is a test example, and we're looping over all test examples. There are capital B of them. And so what we're limiting is the difference in probability, the difference in distribution over predictions made by our model phi for all the test examples, right? And the way we limit the difference in these output distributions is the same as in the standard differential privacy definition, namely through a privacy loss epsilon and a privacy failure probability delta. To achieve private prediction, on a high level, there are two types of methods that you can use. The first type are private training methods. So what these methods do is they train a machine learning model in a differentially private way. So the parameters of this model are differentially private. And because differential privacy is closed under post-processing, what this means is that we can release predictions for infinitely many test examples while still maintaining the differentially private guarantee. The second set of approaches are private prediction approaches. So these train a non-private model, but they're going to apply differential privacy to the predictions of the test examples. And so in these private prediction methods, the information leakage is a function of the inference budget B. So in our study, we looked at both types of methods. In particular, the private training methods we looked at are the following three. The first one is model sensitivity or output perturbation. So the idea here is to train your model and to add Laplace or Gaussian noise to the parameters of the trained model. And this gives you a differential privacy guarantee in case you're using linear models and you're using regularized differentiable convex losses and a few other smaller assumptions. The second method we looked at is loss perturbation. In loss perturbation, the idea is to add Laplace or Gaussian noise to the loss that is being optimized. And this provides differential privacy under the exact same assumptions as the model sensitivity method. The third method we looked at is differentially private stochastic gradient descent, or DPSGD. The idea in DPSGD is to perform stochastic gradient descent while learning, but for each stochastic gradient that's computed, to clip that gradient to have a restricted norm, and to add Gaussian noise to the clip gradient before the parameter update is performed. And this can provide differential privacy even for nonlinear models, although it does require that the privacy failure probability delta is larger than 0. The second set of methods that we looked at are private prediction methods. We looked at the following two. The first method is prediction sensitivity, which is another example of output perturbation, but here the output perturbation is applied to the predictions on the test examples, right? So we train a non-private model, we use this model to make test predictions, and now we add Laplace or Gaussian noise to those predictions before releasing them. And this provides a differential privacy guarantee for linear models, again, that are trained using a regularized differentiable convex loss function. The second private prediction method that we looked at is subsample and aggregate. The idea of subsample and aggregate is to split your training sets into T disjoint subsets. We train a model on each subset, and now we're going to use these models to vote for a certain prediction when we make test predictions. And what we're doing is we apply the exponential mechanism on the model votes. And this gives you a differential privacy guarantee on the test predictions with no other assumptions on the underlying model. So now I'm going to pass it over to Awni, who's going to present the experiments that we performed in our study.
Our first set of experiments were on MNIST with linear models. We trained most of the methods using limited memory BFGS. The only method we did not use this for was differentially private SGD, which was trained with stochastic gradient descent. We cross-validated the amount of L2 regularization for all of the different methods. We first looked at how accuracy changes as a function of the privacy loss epsilon. We looked at this both for a 0 privacy failure probability delta and a privacy failure probability delta 10 to the minus 5. When delta is 0, we cannot use the differentially private SGD method, so it's not pictured here. As we can see in this case, the subsample and aggregate method actually works better than most of the other methods for most values of epsilon. When we allow for a non-zero delta, differentially private SGD actually works better than most of the other methods. It's closely followed by loss perturbation and model sensitivity. In fact, the private training methods work much better in this case than the two private prediction methods. We next looked at how accuracy changes as a function of the inference budget, the number of queries allowed by, say, an adversary. We can see that in both cases, the for both a privacy failure probability of 0 and a non-zero privacy failure probability, the private prediction methods, subsample and aggregate, and prediction sensitivity, the green and black lines here, get quite a bit worse as we increase the inference budget. This is because we need to use a larger noise scale in order to protect the model at the same level of privacy. What we see here for the private training methods is that they're pictured as flat lines, which is because they have essentially an inference budget that is infinite. We also looked at how accuracy changes as a function of the privacy failure probability delta. Interestingly, the private training methods are relatively flat. They are insensitive to relatively large order of magnitude changes in delta. However, the private training methods, the private prediction methods, on the other hand, actually get worse as we decrease delta noticeably. We also looked at how accuracy changes as a function of various problem specifications for fixed privacy parameters epsilon and delta. We looked at, for example, how accuracy changes as a function of the number of training examples. What we see there, for the most part, is that the methods improve, the accuracy improves as we increase the number of training examples. However, the subsample and aggregate method actually plateaus, which is not so desirable. As we increase the number of dimensions, the model size gets larger, and we need to use more noise to protect the privacy of the data. We see here that the two methods, model sensitivity and loss perturbation, get worse as we increase the number of dimensions. The subsample and aggregate method, however, actually stays relatively flat. As we increase the number of classes, in all cases, the accuracy for the different methods gets worse. And this makes sense, since at any query, we're releasing quite a bit more information if we have more classes. And so we either explicitly or implicitly need to be adding more noise to protect the data. Our next set of experiments were on a much larger model, an 18-layer residual network, which was trained on CFAR10. To get this model to work with differentially private SGD requires changing batch normalization to group normalization, since batch normalization depends on multiple training examples, and we need something which we need our layers to only depend on one training example at a time. We trained DP-SGD using SGD as well as subsample and aggregate. The other methods we did not use in this case because they are limited to much simpler models. We looked at accuracy here as a function of the privacy loss epsilon. We see that differentially private SGD actually works better for the most part than subsample and aggregate for most values of epsilon. We also looked at how accuracy changes as a function of the inference budget. In this case, the private prediction method, subsample and aggregate, gets dramatically worse as we increase the inference budget. It's really only better than differentially private SGD for very small values of the inference budget. Again, DP-SGD here is depicted as a flat line since it has an infinite inference budget. In summary, private training tends to be better than private prediction for most settings, really only for very small inference budgets and perhaps for 0 privacy failure probability delta does private prediction work better than private training. We attempted to summarize how the different parameters all relate to one another in this table below. We look at, for example, how privacy loss epsilon can change with certain aspects of the problem, such as the number of training examples or the number of classes, the dimensionality of the input. We also looked at how the privacy budget affects these metrics that we care about, as well as the number of models, which is most specific to subsample and aggregate, as well as the amount of L2 regularization. That's all we have for the trade-offs of private prediction. Thank you for watching.